Today we're going to be talking about continuity. Now, I had a student ask me about continuity, and I asked him, what do you think continuity means? And then he said that continuity is the notion of drawing a graph of a function where you don't pick up your pencil as you draw. Okay, so any function which I can draw without picking up my pencil is going to be a continuous function. Okay, and then he asked, well, what's the need for all the epsilon delta definitions, and where does the rigorous mathematical definition capture this intuitive picture, right? And so that's what we're going to talk about today. So let's begin with the definition of continuity. Specify continuity at a point. So this is the definition of continuity at a point. Okay. So function is continuous at the point x equals a if for every epsilon greater than 0, there exists a delta greater than 0, such that the distance between f of x and f of a is less than epsilon whenever the distance between x and a is less than delta. Okay, so this looks like somewhat of a formidable definition. Let's unpack what this means geometrically. So if I draw my function f, okay, say I draw function f, and I look at a point, okay? Then intuitively speaking, I'm specifying an epsilon error, okay? So I'm specifying an error in the values of my function, okay? Which is like specifying some bar centered at the value f of a. Here's f of a. And this bar is of height epsilon, okay? Well, height 2 epsilon typically. And then the idea is that I should be able to find a neighborhood, in this case, with following neighborhood of A of radius delta, okay? So I find a delta neighborhood of A such that in this delta neighborhood, the values of my function, which are these values in this delta neighborhood, the values of the function are trapped within the epsilon neighborhood of the point f of a. Okay, so this is a local definition which essentially says that near this point f of a, the values of f of x are close to the values f of a. So it's almost a local version of being able to draw your pencil. In order to draw your pencil, you can't teleport from one location to another location. And so locally, at each instant of time, you need that the values of the function are close, in some sense, epsilon close to each other when you're in a neighborhood, when you're in a delta neighborhood, okay? Now notice that this depends on somehow the steepness of the function. For example, if I had a very, very steep function here, and then I specified the same epsilon, okay? If I specified the same epsilon like this, then notice that I'd have to have a smaller delta neighborhood. Okay, so my delta neighborhood that's going to work for this guy is actually going to be much smaller. Okay, so here's my delta neighborhood. And notice that because the function is steeper, its values are changing more rapidly locally, its values are changing more rapidly. And so I need a more constrained interval, a smaller delta to enforce that the values of the function are all trapped within epsilon. So somehow the choice of delta, of course, now I can choose delta to be, I don't have to choose delta to be as large as possible. But somehow the largest possible choice of delta is governed by the steepness of the function at that point, okay? The steepness of the function. So if my function is steeper, intuitively, then to get within the same error bound, I need a smaller delta, okay? So this is going to lead us to a notion of uniform continuity, okay? Which essentially is if I require that if I let x vary and require that my delta should work for all x. So let's discuss this. Okay, so I'm just going to change my definition here. So is uniformly continuous on the domain D if for every epsilon greater than 0 there exists a delta greater than 0 such that f of x minus f of y is less than epsilon whenever x minus y is less than delta and x and y are in not bigger than D. So all I've done is I've let the fixed point A vary in my domain, okay? And then I've required that delta should work for all y. So it doesn't have to, delta does not depend on the choice of the point A. I'm now letting A vary, okay? And so intuitively speaking, if I had a function that looked like this, then, and I specified an epsilon neighborhood, I specified an epsilon error, okay? Then essentially, what I want to look at is for this fixed error epsilon, which applies, this fixed error epsilon, which applies to everywhere on the function, okay? I want to look at the steepest point of the function. So if I look at the steepest point of the function, it's probably like somewhere close to here. And then for this value of epsilon, I know that, for example, this choice of delta will work to constrain, this choice of delta will work to constrain the values of the function at this point, at this specific point y, okay? But now, notice that since this is the steepest part of the function, in fact, you know, if I go over here and I use the same delta, well, that's definitely going to work, right? If I use the same delta, that's still going to constrain the values of the function within epsilon at this point, and it'll work for every point, actually, because this is the worst, this is somehow the place where the function is the worst behaved, okay? And so if I look at this, the place where the function is the steepest, and I choose my my delta to be the point-wise delta at the steepest point of the function, then I can actually move the point around that I'm considering, and this choice of delta will still work for every possible point because I've essentially accounted for the worst case, okay? And so this will allow me to have, you know, if I vary the point y and I vary this delta neighborhood along the graph of the function, then no matter where I go, the values of my function, if I go here, for example, the values of my function will stay within the epsilon neighborhood, okay? So here's the values of the function, and in this delta neighborhood, and the values of the function are clearly restrained within the epsilon neighborhood. So I can slide this delta neighborhood around and ensure that my approximation is within epsilon everywhere for this uniform choice of delta. So the choice of delta does not depend on the point. And somehow this delta is possible if the function has a steepest point, right? And then at the steepest point, we can choose our delta from the point-wise definition of continuity at the steepest point of the function, okay? So maybe I'll go into an example of how this works. But one last thing that I'll note is that a continuous function on a closed and bounded interval is uniformly continuous. Okay, now I challenge you to try and prove this claim, and I'll post a video proving it later on.